Hey friends, welcome to Chemistry Lover, and in this video series we are talking about the aromatic heterocyclic compounds and their reactions. So previously I discussed about pyridine and pyrrole, and in this video I'll be talking about furan and thiophene. Right. Now pyrrole has the structure like this, which is also a 5-membered heterocyclic compound, and all these three compounds has more or less same properties. Their reactions are similar. That's why I will suggest you to first visit this video about pyrrole, because whatever things I discussed about pyrrole I will not again discuss in this video. Only the new reactions or the differences I will discuss here. So first make sure that you watch that video, because that will help you. Now if we talk about the physical properties of furan and thiophene, you can see the oxygen and sulfur both are more electronegative than carbon, so the direction of the dipole moment should be away from the ring, right? It is the inductive moment, because the inductive due to the inductive effect, the oxygen will withdraw electron from the ring. But we have to consider the mesomeric effect also, and if we consider the mesomeric effect, then like whatever we discussed about pyrrole, here also you will have the resonating structure, like oxygen will have negative positive charge and the ring will have negative charge. Similar is the case for your thiophene, and you will get structures like this. So in these structures you can see the direction of the dipole moment should be towards the ring. Now for both cases the mesomeric effect is more important than the inductive effects, and that's why the actual dipole moment direction would be towards the ring. So for all these compounds, furan, thiophene and pyrrole, the direction of the dipole moment should be towards the ring from the heteroatom. So from the heteroatom towards the ring, so this is the direction of the dipole moment. Now let us talk about the chemical properties of furan. So first of all, furan is a very poor aromatic, it has very poor aromatic character. Its aromaticity is very low, and that is manifested by this reaction. So if you just employ some acid, let's say HCl, in furan, what you will get? You will get some product which is where the ring is broken. So you can see the mechanism is, first it will take a proton like this, as what is the case for electrophilic attack. So it will first attack on protons to make this protonated structure. Now water can attack here because this center is positively polarized, so you will get this, right? Now you can see this is a reversible step. So after that, either it can come back to its aromatic form, or it can go this direction. So all these reaction steps are reversible, right? Now actually in the reaction you will end up with this product. So now again you can see protonation can occur here, and this oxygen can push, and you will get this. So now after that, so the same step I am showing here, so this is like this, so you will get this product. So as we are getting this as our end product, this is showing that it has very low aromatic character. So after this protonation step, it has very less tendency to come back to its aromatic form, rather it will react in a forward direction and end up with this product. So this reaction proves that it has very low aromatic character. You cannot get this type of reaction with say your thiophene. So thiophene has more aromatic character than furan. Another example of the same thing can be explained here. So you can see, if you just add bromine and methanol here, what you will get is this product, right? So this product you will get. What you expect? You expect bromination like this. So you may expect monobromination or multibromination, that is another matter, but what you expect is bromination. But instead of bromination you will get this product. Why it is happening? So in fact in the first step it will attack on bromine like this. So let's say here you have the bromine, So in the first step it will attack on bromine to give you this intermediate, but after that, as you have methanol in your reaction medium, this methanol will attack here to give you this intermediate. Now this oxygen lone pair is very powerful, so it can kick off this Br minus like this, and you will get this intermediate. Now again this methanol can attack here to give you this product. So you can see in this particular step, what can happen is that you have this hydrogen, and this hydrogen can go as a proton, and this can come back to give you this product. This was a possibility that you get bromination, but there is a competition between two steps, either this deprotonation or the attack of this methanol, and you can see indeed this attack of methanol molecule occur, and that proves that it has very less tendency to get back its aromaticity, rather it will prefer to react with this methanol. So this again proves that this furan ring has very low aromatic character, and this is a very interesting compound. You can think that if we hydrolyze this compound, you may get this di keto product, or in this case it is aldehyde group, but actually this is a very unstable compound. So if you add H plus H2O, it will happen, but just after making it, it will be again hydrated, or some other nucleophile will attack here, so it is very unstable, but it is a synthetic equivalent of this compound, so we can use this as a synthetic equivalent of this, and this thing we will show later. Now you can do bromination of furan if you don't have a solvent like methanol. So in a non-protic solvent, or solvent like, for example, let's say you use thiophene, or sorry, not thiophene, let's say you use THF. So this type of solvent if you use, which has very low nucleophilic character, very unreactive, they can in that solvent this bromination can be possible, and in this case you will get multi bromination. All these four positions will be brominated because it is a very reactive species. This oxygen lone pair is very much reactive, so you cannot get monobrominated product. Now another reaction which proves the low aromatic character of furan is this reaction. So if you just add H plus and water in your substituted furan, in this case we took a substituted furan where you have two methyl groups, so you will end up with this non-aromatic and non-cyclic product. So how this reaction is happening? Same mechanism. First the protonation will happen here, so you will get this. Now this water molecule will attack here to give you this. So again you can see this proton can be expelled out to get back its aromaticity, but this step, this is a reversible step, but this step is very unfavorable. That proves that its aromaticity is very low, and it will go in the forward direction. So again here protonation will occur, and this lone pair will push, so it will give you this, and after that you can see water molecule is there, so isomerization can take place like this. Always this double bond will shift towards the conjugation, so it is now conjugated, and now this ketoenol tautomerism will give you this product, right? Then this is another example where you can prove that furan has very low aromatic character, and in this case you can see this substituted furan, if you treat it with H plus in methanol, you will get this non-cyclic and non-aromatic product. So how this reaction is happening? In the first step the protonation is happening, and in this case it is going through a conjugated resonance. You can see this is how the protonation is happening. So here you have two hydrogen atom actually. Now after that what is happening? The methanol molecule is there, so methanol molecule will attack here to give you this. Okay, now this oxygen lone pair will push, and it will take some proton from here, so now it can go ketoenol tautomerization to give you this keto, and another methanol molecule can attack here to give you this. Okay, now this is a protic solvent, right? So here you have protons, and this type of isomerization is always possible to give you this, right? Now this will push its lone pair here, and it will be protonated like this, and after that you can see this basically hydrolysis. This is a tetrahedral intermediate type structure, so hydrolysis of it will give you this ester group here, and this group can again tautomerize to give you this keto product. So again this proves that aromaticity of this furan ring is very low. Now let us talk about the reaction of thiophene. So can we break the aromatic ring of thiophene like this? The aromatic character or the aromatic ring of thiophene can be broken, but not like the previous way, because protonation of this molecule is slightly difficult, because this sulfur has 3p orbital here, and that has very low tendency in coming to conjugation. So it can be done in another way, that is using this catalytic condition, that is Raney nickel, which is a hydrogenating condition, and hydrogenation with Raney nickel will break the uh, whole molecule to give you this, and this can be used in preparation of useful molecules like this. So first here these two groups are put here. There are some reaction condition I will discuss later, and then you can see when we employ the Raney nickel condition, this ring will be broken to give you this product, right? Then another interesting reaction of furan is, you can see this furan is oxidized with DMDO. This is called DMDO, dimethyl dioxyren, and this oxidation will give you this interesting product. Okay, this is basically the same reaction which I discussed. So in the previous case I discussed about this reaction where I told you that this is a very interesting compound, and you can use this one as a synthetic equivalent of this. And in this case we are really getting this compound while we are oxidizing this furan with DMDO, so it will give you this. Now here you have two aldehyde groups, and you can do Wittig reaction with this aldehyde group to give you this. Now in this case you can see we used the stable ylide, and that's why we are getting the trans product, right? Now these are the normal reactions of furan and thiophene which I discussed for the pyrrole also, that you can do, you can put on some acyl group, that is acylation on furan with zinc chloride and acetic anhydride. Now you can see we don't use aluminium chloride here because they are strong Lewis acid. We need some weak Lewis acid, because otherwise it will it will be over reaction. So we want only one substitution, that's why we used the weak zinc chloride Lewis acid, and the reaction is also done with 0 degree centigrade temperature, you can see. But thiophene is less reactive, and in this case you have to use 100 degree centigrade temperature to do the same reaction. Now if we want to do nitration of furan, you can see we can't use the usual nitrating condition, that is HNO3 H2SO4, because that will break the ring. We already told in proton the ring is broken, right? So we have to use the mild condition like this ACONO2, which we used for the pyrrole also. But in this case this pyridine is important, presence of pyridine. Without pyridine the reaction will not happen. Why this is so? So this will be cleared by this mechanism. So you can see the first step is attack on here to give you this intermediate. Now the OAC minus which is removing in this step, that OAC minus can attack here to give you this. Okay, so I already told that the pyrrole the furan ring has very low aromaticity, right? So instead of going back like this, it will prefer that the OAC minus will attack here. So if you don't have pyridine, you will get this product. Now if you have pyridine, what can happen? Pyridine is a very good base, you know, and in this case this nitrogen lone pair will take this proton, so it can kick off this OAC group, and you will get back your desired product like this. So the presence of pyridine is very important. So while you will write down this reaction, you have to always mention the presence of pyridine, otherwise it will be wrong, right? Then the metallation can occur with furan and thiophene as like the same way with pyrrole. You can see if you use BULI, you will get the metallation over here, that is 2 position, and the same is and the mechanism is basically, first this oxygen lone pair will coordinate with this lithium. Now this Bu group will take this hydrogen and it will go as BUH, so you will get lithiation over here. Now you can use this with various type of reaction, any electrophile you can employ, and it will add to this electrophile. For example, you can use RCOCl. So in this case here it will be this acyl group like this. Now what you have to do when you want to do lithiation over here? So in this case you have to use this type of compound, so where you have some halogen atom over here. In this case it is a bromo compound, and if you add butyl lithium at very low temperature, for example minus 78 degrees centigrade temperature, you will get lithiation over this 3 position. But you have to be careful that if you allow this reaction to stay for long time, for example if the temperature goes above 40 degrees centigrade, then isomerization occur and you will get again the 2 lithiated product. So you have to immediately add Bu3 essential to your 3 lithiated intermediate, and it will capture it like this. So now you can use this compound for your further reaction, so you will get substituent over this 3 position. And the last topic related to this I will discuss is the pericyclic reaction. So both furan and thiophene undergo pericyclic reaction, but you can see this oxygen lone pair is very much reactive here, and it will rise the HOMO energy of HOMO of this particular compound, and that's why you have to use some low energy LUMO, right? So low energy LUMO means you should have some conjugated dienophile. For example in this case this dienophile is conjugated with these 2 carbonyl groups, so it will react with this maleic anhydride to give you this product and this product. So this is the endo product and this is the exo product. So you can see in this case 2 products are possible, the endo product and exo product. In the endo product these 2 carbonyl groups are in the same direction where this double bond is there, so they have the endo relationship, whereas in this case you can see this is below the plane and this is above the plane, so this is the exo product. And we know that following the endo rule always the endo product is favored, but in this case we get this exo product as major product. Why this is so? Because this exo product is thermodynamically more stable, this endo product is basically the kinetic product. In the transition state structure, due to the presence of this carbonyl group and this developing double bond, there is a pi stacking type interaction, and that will stabilize the transition state. But when you consider the stability of the product, the exo product is always sterically more stable, right? Now this reaction is reversible reaction, okay, and both, so after forming this product they can come back like this. So it can again push here, for example it can push here and you will get this starting material back. So this reaction is happening in a reversible way, and in a reversible reaction we will get always the more stable product as our major product, so that's why we will get the exo product as major product. So this thing you have to take into your mind. And for thiophene you cannot get the Diels-Alder type reaction with thiophene. You can see if we add thiophene in this maleic anhydride and we heat, we will not get any reaction, because this thiophene has the higher aromatic character. You know benzene will not undergo Diels-Alder reaction, it cannot act as diene, right? In the same way this thiophene also cannot act as diene, because the aromaticity of thiophene is very close to benzene, although it is lower than benzene, but it is very close to benzene, and that's why you have to first destroy this sulfur lone pair. So for that we have to oxidize this compound, then there is no lone pair available for this aromatization. Now this will act as normal diene, and you can react it with a dienophile to give you this type of Diels-Alder adduct, and then this extrusion reaction can happen, and here sulfur dioxide gas will go and you will get this aromatic compound. So thiophene will only undergo Diels-Alder reaction in good yield when you have this alpha lone pair unavailable, you somehow make busy this alpha lone pair. So these are the useful and important reaction for thiophene and furan. In the next video I may discuss about indole, or I may discuss about the miscellaneous reaction of the previous topics, that is pyridine, pyrrole, thiophene and furan. There are a lot of other reactions which I didn't discuss, and I will discuss them in one video. So thank you for watching, and if you are new in this channel then subscribe my channel.